Very good evening, everyone, and very good evening for the organizer. Thank you so very much for this. I think that this topic is very interesting one. It is in general applicable to all of us engineers. What it takes to be a good engineer. Now, I myself particularly belong from the electronic industry, and that is the reason I have chosen it to be specifically for the electronics engineering. But then in general, I think we all, after doing our engineering, we all have this fundamental question, right? What we have learned in our college, in our 4 years of graduation, is it really worth, or how valid is that when it comes to industry application? And if yes, or if let's say I have to do anything beyond that, then what is the scope? What are the other things that I need to expertise myself with so as to be a good engineer in the industry? So ultimately, after our graduation, the key focus for many of us are towards the industry, being a good engineer there, having a good job with a good reputed company. That's one of the dream. At least when I was doing my engineering, that was the dream that I personally had. And I know many of you also might be having the dream of starting off your own engineering firms. So basically something to do with engineering, something of your own. So irrespective of what your ultimate dream is, when I say the term industry, what I mean is both the scenarios, whether it is your own startup or own engineering firms versus, or whether it is your job at some of the companies. Okay, so let's get started. So the agenda, I have tried to keep it very simple. First, directly to the topic. I'll come to the topic where I would be talking about what it takes to be a good engineer. And then, it is one thing to say it, and it is another thing to actually walk the talk. So I'm going to say a few things on what it takes to be a good engineer. And then I'm actually going to take you through a process of simple example where I will tell you how that approach, the fundamental approach to be a good engineer that I shared in first couple of slides, how that actually we can apply or how it actually applies when it comes to the actual practical engineering. Okay, so that's what I am calling it as a let's solve it together. So together we will try to solve a very simple example to bring about the idea of being a good engineer. And next, given that I am from the industrial background, having almost close to 10 to 11 years of experience in electronic core industry, I thought there's a great opportunity for me to share my experience and also guide you through what are the career options that you all have as an engineer. Okay, and of course, currently under this current COVID condition, right, we all are having this thought in our mind that COVID-19, how is it going to impact our industry? Is it in a future-wise, is it looking bright, or do we have certainty in terms of jobs, or what is it currently? So I would share some of my insights related to that as well. So with that, let me get started with the first topic, what it takes to be a good engineer. Okay, so now I definitely didn't want this session to be a very formal session. I personally don't like things to be very formal because that makes it boring. And most of the time in our engineering colleges, as well as in our engineering studies, even during some of the lectures that you watch online at various places, things tend to be a little boring when it comes to engineering or in general studies. And that is the reason I wanted to take a slightly different approach. I wanted to show that study and engineering is not actually boring, rather it's a fun if we really get the actual hang of it. Okay, so I think stories are something that we all like, and I also wanted to start with a story, and this is a story related to my own life. So I thought that this will be a good platform where I can share, and from there I would bring about few points which eventually will align with our main objective. Okay, so the first story that I want to share with you is about biogas. Okay, now Turning Point and biogas. Turning Point is one of the program that used to come in DD National almost 10 years back, 10, 12 years back. At that time, there were no other channels available. At least I am from a village background, so at my area, there were no other channels. The only program we used to get was Doordarshan, and Turning Point was one of my favorite programs. It's basically, it showed various scientific principles that was there at that time. and it gave a demonstration of those principles as well. So it was something that I was fascinated. Okay, and one such program of Turning Point, they actually gave a idea of how the biogas is getting generated. So I think the basic idea of biogas we all are familiar with. Let me take out my pen. I think we need to do for the biogas is uh, collect some cow dung or any other biodegradable product and then put it into a closed container. And here the biodegradation happens. And in the process of biodegradation, it releases a inflammable gas. And finally, that's what we can use for our cooking purposes. So the idea is very simple. And I think almost all of us are familiar with this idea. Now, when I first saw this idea, right, at the program Turning Point, it really intrigued me. I really was very excited at that point of time because, from my background, given that, I used to stay in a village, my mother would be using those coal-based furnaces where there will be a lot of smokes coming out, and every evening the entire house will be filled with smoke. She has to keep it outside. She has to carry it in the after a couple of hours, and then the entire cooking process will start. So that's when it was a eureka moment for me that biogas is something I can easily make. Now I know the concept. So why not help my mother with the biogas and solve her problem? And that's when I started with my project. And what I did is I tried collecting cow dung, and it was not at all a difficult task at that time because you all know, right? At village, I think cow is one of the common thing that you find. Livelihood of village depends on cows. There were a lot of cows in and around, so it was very easy task for me to collect a huge lump sum amount of cow dung. So I collected it, and then the second task was to get a closed container. So I took a bucket. I think we all know those plastic buckets with closed lids, right? So I took a big bucket with those closed lids, which was there at home. I put all the cow dung inside that. I closed the lid. I put sellotape, tried to seal it. And now it was only this last task that was left for me was to just keep it for a couple of days, let it degrade, let the gas get accumulated, generated. And then I will, surprise my mother with the biogas, and she'll be all happy that, her son is actually helping her. So through science. So that was really an awesome moment for me. And I was very excited. So now the one key thing was that I had to somehow hide it from my father. So what I did is I took that entire bucket of biodegradable cow dung bucket, and I put it inside below the pillow of my father, because I think that's the safest place. He will search everywhere, but he will not search below his bed. So I think that was the best place. So I hid it there. It was all good till this point, but unfortunately, I forgot all about it in a couple of days. My interest went into something else, and I completely forgot all about it. And eventually, that biodegradable product started releasing its gas, and the entire house started smelling like the cow dung is everywhere. It was smelling so bad everywhere. And that's when everybody in my house started searching what's happening. I was still in my playground and playing. I had no idea of it. I just come back home and I see that something is happening at home. Everyone is all around searching for things. And that's when my father realizes that the smell is coming from his room, and particularly below his bed. And then he figures out that below his bed there is a bucket with all the cow dung completely decomposed and releasing smell all around. And immediately he knew that it was not done by anyone, no one else other than me, other than his own son. So, okay. So immediately he realized, and the chasing started. I also realized there was no communication. It was only eye contact. He looked at me, I looked at him. He realized I did it. I realized he now knows, and I have to run. So that was the moment of biogas and Turning Point. Another story of my life is again on the similar line. Again, Turning Point is my life changer. So again, that science program, this time they showed how to make battery. Now, at my village, it used to be a common norms that every day, almost evening, 6 to 8, there will be 2 hours of power cut. Sometimes it used to be even longer. And that was the prime time for us to study or do anything, right? So it used to be a problem. It was very dark, sometimes hurricanes or lanterns, sometimes oil will not be there. So it was a problem. And I wanted to solve that problem. The moment I saw this battery concept, I realized that this is my second opportunity to actually solve a problem and help everybody around. The idea of battery, I think we all know. By the way, I've used two terms here. One is the battery, another term is cell. And I hope you all know the difference between battery and cell. If not, let's discuss maybe at the end. Okay, so I want to do make a battery. The concept was very simple. You take a copper plate, I think we all know, you take a zinc plate, and you put it inside a liquid or diluted H2SO4. And then it develops a potential across it. And once you connect a bulb or a LED across it, it's going to glow because there is a potential difference between them. Okay, so that simple idea I wanted to implement. So my quest started towards making the first battery of my life. Now, I wanted to collect all the ingredients. So collecting zinc was a very simple task because I think I knew that all the pencil batteries, all the outer surface of the pencil batteries are made of zinc. And there were so many dead pencil batteries at my home. So I just broke those dead pencil batteries and I got my zinc. It was very simple to get my zinc. Challenge was to get the copper and to get the H2SO4. Now, for the copper, I had, again, brilliant idea. I realized that my mother, in her temple area, all the cutleries that is there for puja, right, for puja purpose, are made out of copper. So the spoons and those plates and everything was made out of copper. So I happily entered into the temple area, and I took one copper spoon. I told God, this is for science, please forgive me. And I immediately ran from that place. So copper plate is done, that spoon gifted by God, and the zinc from the battery. Now, the next thing was to get the acid, diluted H2SO4. And that was a very big challenge. I went to different chemist places, asked for H2SO4. Nobody helped me with that because I think H2SO4 in general is very risky because if it falls on your skin, it will burn. And those burns are not even normal burn. It's a very dangerous burn. So one has to be very careful with H2SO4. And me being a kid, they didn't trust, they didn't give. So how do I solve the problem of acid? My creative brain started thinking. And that's when I realized that, again, from some science book, I read that if you have some place where, let's say, water is accumulated for a very, very long time, it tends to become acidic in nature. So I was thinking that, okay, maybe some drainage somewhere where the water clogging is there for years, maybe that water could be acidic in nature, and maybe I can use that for acid. Why not? And with that thought, one fine day while coming back from school, I saw a drainage place, and it was looking all green, and towards the end, there was some black water. And I thought that that's the water, that's the acid for me, and I wanted to collect it. So I started walking on that green grass. But unfortunately, it was not a green grass. It was complete mud. And on top of that, there was this green grass layer. And then I completely went inside it. And I had a white color school shoes, newly bought just a couple of days back. That completely turned black. And I washed it again and again. But it remained black. It was so bad. And my father eventually figured out what I did to the kids. And then again, the cycle of beating and chasing started. Okay, so that was story number 2. Now you may be thinking, out of these 2 stories, what is the moral? What is the ultimate summary that I should take? Of course, to put it in a scientific term, I try to make this language very formal and scientific. Make sure you wear a Karna Kavach Kundal. Basically, Karna is our mythological character, right? So he had a kavach. So you have to have that kavach, okay? And not Iron Man. I like Indian version. Indian heroes, not outside. Okay, so while doing any experiment, so as to protect yourself from any external impulsive force that might be applied on you, also known as beating from parents, at the end of your experiment, in case any disastrous outcome at the end of the experiment. Okay, now jokes apart, this is not the actual moral of the story that I wanted to highlight. The moral is actually this. The real observation here is to see why I started with the design of biogas or the battery in the first place. Why? I think the reason why I shared those 2 stories is to bring about the true essence of engineering. And I thought, why not share those stories, and through those stories try to bring about that particular essence of engineering. So if you think here, why I started with that biogas project in the first place, to solve the coal-related smoke problem of my mother. She used to suffer from smoke, and she used to cough a lot. So I wanted to solve that problem. And that's when I started with that biogas project. Second, the battery, manufacturing the battery. Why did I start with that project, or what drove me towards making the battery? The concept or the problem that drove me towards that was to solve the problem of power cut at the evening every day. Okay, it was a struggle for all of us. So having a dark room sometimes hurricanes, sometimes not even hurricanes. It was a problem, and I wanted to solve that problem. And if I could make a battery, it would actually solve the problem. And that's when I started. So the reason I started both the project was to solve two particular problems, and that is the true essence of engineering. Okay, it not only applies to those two stories in general. Even today, at the industry level, when I design something, right, I have nobody tells me that here it is, use this component and design this. It always starts with a problem. So anything and everything to do with engineering starts with a problem. Okay, I'll come to the true essence of it in a while. I'll go a little bit more deep into it. And we engineers try to solve those problems by the help of application of science. These two keywords actually summarizes the entire thing. One is the problem. Problems are good. Okay? You want the problems to be there so that you can solve them. And second is application of science, not just knowledge of science. See, if you just know the concepts, if you just know the scientific principles, it doesn't make you a good engineer. You have to have the aptitude towards how do you apply those concepts or how do you apply those scientific knowledges to solve a particular problem. So let's say, for example, why those two stories? Let's take a realistic example. We all use mobile phones, right? And recently, you have known that two phones manufacturer in particular, a couple of phone manufacturers in particular have become really famous, right? Xiaomi, Apple, couple of high-end companies as well as mid-end companies. We all know, right? So, but before that, there was another brand called Micromax. Okay, but nowadays you don't truly hear much about Micromax. Whereas couple of years before, they were dominating the market. Even a couple of years before, I think Nokia was one of the common names that we all have heard. Definitely, they were the pioneer towards mobile phone. But nowadays, you hardly hear about Nokia, though they are trying to come up with some of the phones. But ultimately, it's dominated by other players in the market. So what did they do? When you go to buy a particular phone, do you really care about whether it is coming from either of the companies, any of the companies? No. For you, what matters is how good the performance of the mobile phone is. Okay, and these companies try to take those target requirements, came up with the problem definition that they need to solve, the challenges that they need to solve to satisfy the end customers, and finally they applied the scientific principles to come up with the solution. And that's when the companies who successfully did that grew, captured the market, and the companies who failed to understand the true customer need, who failed to understand how to solve those problems by applying the scientific principles, they couldn't sustain themselves in the market. So these two keywords, always remember, okay? Problems are good. Because problems exist, we engineers exist. And application of science, again, not just knowledge of science, application of science. That's the essence of engineering. So the right approach, learn the knowledge of science in a way that you can apply them to a given problem and come up with a solution. Okay, this is what I understand. This is what is my way of defining what it takes to be a good engineer. You need to know the concepts. Definitely, knowledge is important, because if you do not have the knowledge, you can't apply the same, right? At the same time, if you restrict yourself only at the knowledge level, which typically happens in our engineering college environments, right? All we do is we just study the books. At the exam time, they will ask us some question. We will just try to answer something that we have studied from the book. We never truly think that how we can use those principles of science to actually solve a practical problem. And that's the aptitude that we need to develop. And though in engineering colleges, through lab experiments, they try to build it, but unfortunately, our current grading system and all this competitive approach even spoils that. We tend to move towards how to get a good grade, and we really do not bother about learning this aptitude towards how to apply those knowledge to solve a given problem. And at industry level, this is what is needed. Okay, you have to know, and you have to know how to even apply them. This is the making of a true engineer. Any engineer who is actually capable of doing this is going to thrive, really do well at industry level. Because at industry level, no one is going to come and tell you that, okay, do this steps. I will evaluate you based on these steps. No one cares. All they will do is they'll give you the problem statement. Hey, currently the network is 4G, which has certain speed, let's say 5 Mbps speed. I need to increase the speed to 20 Mbps, 100 Mbps. And that's when the concept of 5G, which is coming up. So that means 4G to 5G is definitely a data rate increase, right? 3G to 4G, we all know that how much mobile internet speed increased. So when you talk about 5G, no one is going to tell you that do this, and then you will reach to 5G. No, they will tell you the end requirement is I want 20 Mbps speed on my mobile. Okay, and how do I achieve that? And from that problem statement, you derive backwards towards the solution by applying all the scientific principles. And that's when you implement those circuits to solve those particular problem. You come up with the 5G solution, and finally you deploy that solution to actually come up with your final product. And that's when you move towards market dominance. And as an individual, you become a truly good engineer. What it takes to be a good engineer? Just to summarize, your ability to identify a particular problem, you need to identify the problem, and your ability to apply the knowledge of science to solve the problem. I think so far so good. I think key point of what it takes to be a good engineer is well understood, well highlighted. Now let's do the walk the talk. Okay, so let's solve the problem and try to see how, it is one thing to say, you may think that, sir, it's all this philosophical talk is good. You are telling us to actually solve or apply the concept to solve the problem, and that's the skill of a true engineer. But how do we actually do it when it comes to actually implementing it, how we think differently and how we do it? And that is why I wanted to walk the talk, and I wanted to give a demonstration or an example through which I'll try to explain the concept. Okay, let's go a little technical here. Okay, this is an example of a MOS transistor. I think we all, I'm assuming that we all have the background of simple plain MOS transistor. And this is the characteristics of a MOS transistor. And we all know there are few regions. Okay, this region is where we call it as a saturation region. This region is the ohmic region, and this region is the cutoff region. Okay, for those who do not have the background of a MOS transistor, I'll just quickly try to summarize the background here. MOS transistor is one of the key electronic component that you use to build a electronic circuit or come up with some amplifiers or transmitters or receivers. Nowadays, we don't use those BJT transistors, very rare. Mostly at industry level, we use MOS transistors. Okay, and this axis, this x-axis that you see here, this x-axis is the voltage VDS. Okay, the drain to source voltage, the source voltage between drain and source. And these different graphs that you see here, right? This is for different VGS. As you can see that VGS is written. So basically the gate to source voltage, whatever is the difference. I think there is some shift in terms of the letters here. Don't bother, there's some shift. This VS should have been here and VG should have been here. I don't know, I think some problem with the slide. Okay, so idea is this VGS. So now, of course, this looks very complicated. And whenever our engineering starts, first time when you have been introduced to this concept of MOS, this graph is what is given to us, and we all panic at that moment itself. Some of us struggle to get this into our head. Some of us we don't. Okay, I want to solve this particular notion, and I want to actually show you that how simple it is to truly understand the concept of MOS. Okay, so to do that, first I will take you through the textbook approach, or take you through how we have seen it so far. Okay, and then I will bring about the intuitive approach. See, the way I talk about electronics, right? It's like, I call it as a feeling. Yeah, we need to feel the circuit. We have the emotional connection towards the circuit. Whenever you think of a problem, the circuit topologies or circuit approaches that you need to do to solve that particular problem should automatically come in your head. That's what is the skill that you need to develop, and that's what is called intuitive thinking. You need to develop the idea of intuitive thinking, how you can think without the equations. See, when you try to solve a particular problem, right, you never use the equations to solve that particular problem. You first think intuitively, come up with an approach to that particular problem solution, and finally you get into the rigor and prove that your thought is right through those mathematical equations. Okay, whereas in academics it happens other way. You are given the equations and then you are told to solve a particular problem. But in actual application, in reality, when it comes to actually designing a circuit, you don't do that. What you do is you come up with the intuitive approach towards solving the problem, and then you get down with pen and paper. So let's see how to approach this particular problem, thing, transistor analysis in a very intuitive approach. First, textbook approach. This is what we all see in our engineering classes, and it always scares us. Okay, so the idea is your VDS. There are, as I told you, right, there are 3 regions of operations. I think that's something we also, the fundamental things is the 3 region of operation: triode region, saturation region, and then there are a bunch of equations that drive or that controls or that governs which region the transistor is operating at. VDS, that is the drain to source voltage. When it is less than VGS, that is gate to source voltage, minus VT. VT happens to be the threshold voltage of this transistor. So think of this transistor as a device which needs a minimum voltage for it to turn on in the first place. Okay, and that minimum voltage that is needed for this to be on is what is called as a VT. So of course, if you hear about all these terms, VDS, VD, VGS, less than VT, it is always a confusion. And that is why I wanted to first bring about how we are conditioned in our academic years to learn the concept, and how we should actually approach it in a different way to make it more intuitive, so that our brain can think on those lines when it comes to actually doing the circuit. So of course, all these things, equations finally simplify your VS cancels, it finally simplifies to this, blah, 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 all these things. I'm not interested in this math. I just put it here so that we all understand what is the rigor that actually is needed to understand the 2 region of operation. And definitely that's not an easy approach. Okay, now let me give you a intuitive approach towards finding out what is it, how do I identify whether a given transistor is in a particular region, whether it is saturation region or linear region, or it is in the cutoff region. Okay, so here again in this page I'm just summarizing the 2 conditions that you need to satisfy, but at the same time I'm not bothered about it. What I'm ultimately bothered about is this expression, and that too not the equation of this particular expression, but a literal interpretation of this expression. What is that literal interpretation? Let's come to that. Okay, so these 2 conditions, mathematical equations. At the same time, I'm not interested in the mathematical equation. What I'm interested is in the literal description of that. Okay, and this is how I have described that, or this is how. So this is the approach that we all need to take whenever we see equation, right? It's not just sufficient to memorize that equation. We have to actually intuitively understand what that equation is telling us. Okay, that meaning is important. I sometimes, as I told you, that you have to feel the circuit, and sometimes, we all have feeling towards our parents. We love somebody, we have feeling towards that person. So in a real life, we all understand what is called feeling, having a feeling towards it, right? But when it comes to engineering, we all feel it like it's abstract. It's like all difficult, gray and white, all boring equations. Not really. I feel towards circuits. Okay, whenever I see a circuit, it talks to me. I get to know. It tells me how to analyze. It gives me approach, and that is what is the intuitive approach that we all need to understand. So let me quickly interpret this. The interpretation of this is, once a NMOS transistor is on. Now, what does that mean? That means you have applied the VGS greater than the threshold. So basically, you have made the device on. If the drain voltage, okay, goes below gate voltage, okay, remember the 2 voltages that I'm talking about? I'm talking about the gate voltage and the drain voltage. As of now, I don't care about the source voltage. Okay, so these 2 equations I'm interpreting. If the drain voltage VD goes below the gate voltage VG by a magnitude more than the threshold voltage VT, then the transistor would get into a triode region, else it will be in the saturation region. Now let me explain myself. Now, this is where Batman comes to save you. You will remember this statement. I will come back to this statement and I'll actually show you what did I mean by that. So let's take a simple example. Okay, I have drawn a potential scale. Now, what is this potential scale? Let me quickly brief you. As you go down the scale, right, it kind of represents at what potential we stand. So that means at the bottommost, I took this as 2 volt. At the topmost, it is at 9 volt. And as we go down along the scale, it is at various voltages. It is just a graphical way of telling you at what level my VD is. If I put an arrow of VD at 8, that means my VD is at 8 volt. For example, here you see that the VG arrow is at 6. So that means my gate is at 6 volt. And as you can see that my VS is at 2. Now, of course, that means the VS is at 2 volt. Now you may say that, sir, how do I know this VD, VG and VS voltage in the first place? I'll come to that. I'll come to that through an example. For now, let's assume that you have been given the VD, VG and VS voltages. And all we have to do is we have to figure out which region the transistor operates in. Okay. If you try to go by the equation, it is going to mess your head. You will never be able to intuitively have a feel towards how to figure out the region of operation. Okay, which is very important when you actually go and try to design some amplifiers or go and try to design some filters. We will have to figure out this. So let's see how intuitively we can go. So as of now, you see my gate voltage is at 6 volt. Okay, my I think these annotations, let me just erase them because I have my own annotations present here. So gate voltage is at 6 volt. Let's say drain voltage is at 8 volt. Okay, and what do you observe? Objective is to find out the region of operation. So if you can see there, here I have summarized that statement that I told you in the previous page, right? The Batman dialogue. Once the NMOS transistor is on, the drain voltage VD, if the drain voltage VD goes below VG by a magnitude more than the threshold voltage, then the transistor will get into a triode region. So that means this is my drain voltage, which is currently at 8 volt. This is my gate voltage, which is at 6 volt. So that means gate is at 6, drain is at 8. Now you tell me, the drain voltage is greater than gate voltage or lower than gate voltage? It is greater. Okay, 8 volt is higher than the 6 volt. So that means which region the transistor will be operating in? The transistor is going to operate in saturation region. Okay, why saturation region? Sorry, I think my slide is hanging. Saturation region. Why? That's the condition that we interpreted from those two cryptic equations. What is the interpretation? As long as my drain voltage is above gate voltage, okay, it doesn't matter at what voltage the gate is, whether it is 6 volt or 5 volt or 4 volt, it really doesn't matter. 6 volt is an example that I have taken. The idea is this: as long as my drain voltage is above gate voltage, okay, it is going to be in saturation region for sure. Okay, and now let's try to simulate that and see. So I do some change in the circuit. As a result, my drain voltage comes down to 7. Is the transistor in saturation? Yes, because my drain is still above gate, so it is in saturation region. Now I further proceed, and my gate voltage remains same. Now my drain voltage has come down and it has become equal to the gate voltage. Is it in saturation or is it in not in saturation? Remember this statement. Okay, we have had, as long as if the drain voltage goes below gate voltage by a magnitude more than the threshold voltage. Okay, this is the interpretation. So as of now, has it gone below? No, it is still equal to gate. So that means it is still in the saturation region. Okay, it is still in the saturation region. Now let's go to the next simulation. Here, look here. So here, the drain voltage, sorry, I think I have missed the arrow is here. So here you can see that my drain voltage has gone below gate voltage. Okay, so originally it was at 8, it was in saturation. Then I did some change in the circuit because of that the drain voltage came to 7. Still the transistor is in saturation. Then I did further change in the circuit. Now what change can cause this? That is a separate question. We'll discuss that. But let's say I did something, my drain voltage become 6 volt equal to the gate voltage. Still the transistor is in saturation. Now the drain voltage has gone below the gate voltage. Okay, but even if it is below, here the threshold VT is given as 3 volt. How much below it is? It is only 1 volt lower, correct? It has gone down by only 1 volt. So that means, has it gone down by a magnitude more than this 3 volt? So that means if I take this 3 volt, then what happens is, if it is 6 volt, and then if I have to take a point which is lower than 6 volt by a magnitude of 3, that means it has to be somewhere below this 3 volt level. Okay, 6 minus 3 is 3. So that means as long as my drain voltage is not going below the gate voltage by a magnitude equal to the threshold, which is 3 volt, I am still in saturation region. In this case, it has gone below, definitely, but it has only gone below by 1 volt and not 3 volt. It has to go at least by 3 volt for it to come out of saturation and get into other region, linear region. Now let's take the same next simulation. Now I did some more change and the drain has gone to 4 volt. Can you tell me whether it is in saturation or in linear? It is still in saturation. Why? Because remember, for it to go out of saturation, it has to go below this voltage level. Right now, it is below gate, but the difference between the two voltages is still smaller than 3 volt, the threshold. And that is why it is still in saturation region. I'm not talking about any equation here. Don't bother about any equation. Just the actual intuitive understanding of the same. Okay. And next, let's take this condition. In this case, as you can see that my drain voltage has gone below this guy. Okay. And this time it is almost gone below by 3 volt. Okay. 6 volt minus 3 volt, 3 volt. The delta between the two voltages is 3 volt. So in this case, can you tell me the region of operation? Okay. It is at the absolute limit. So that means till this point it is still in saturation, but it is at the absolute limit. The moment it goes below this, any voltage slightly below this, it will come out of saturation and it will get into the linear region. Okay, and that is what is my next simulation. This is where I have shown that my drain voltage has now, the drain voltage has gone to this level, which is below this 3 volt level. So that means my gate is at 6. Right now this has come to this level. So that means let's take this as some, say, 3.5 volt. Okay, the delta as 3.5 volt. This point I am taking it as it's 2.5 volt. So that means the delta has come to 3.5 volt. Now this 3.5 volt difference is greater than 3 volt. Okay, and the transistor now is out of saturation region and it has gone into the triode region. So now, to put things very simple, right? Whenever you see such problem, the way you have to interpret this is you have to have the idea of what is that limiting voltage. In this case, this 3 volt is the limiting voltage. How did I arrive at this 3 volt? Because my gate is at 6 volt. My threshold is at 3 volt. So that means my important voltage level or the key voltage level here is the 3 volt voltage, which is 6 minus the threshold, which is 3, and that finally gives me equal to 3 volt. So that means once I know this threshold voltage, right, I don't need to bother about any equation. I simply need to see where my drain voltage is. Is it equal and above in this side? If it is equal and above in this side, I am always in saturation region. There is no equation involved. And if it is below this voltage in this side, any voltage below this voltage, so that means 2.9 volt, 2 volt, 1 volt, 0.5 volt, even negative voltage, it doesn't matter. As long as it is below this threshold point, it is in the triode region. So all those explanation right now was to build to this particular point. Once you know this intuitive approach, you don't need any equation. You don't care about anything. All you need to know is, your gate is at 6 volt, your threshold is at 3 volt. So your key voltage level is 6 minus 3 equal to 3 volt. And as long as your drain voltage, as long as your VD is above or equal to that voltage, you are in saturation region. And the moment it goes below that particular voltage level, you are in the triode region. I don't care about source voltage. It didn't even come into the picture. Okay. In this equation, you will see VGS, VDS, and all those complications, but you don't need to bother about anything. Let's change this problem slightly and take another example. Let's say my gate is at, say 4.9 volt. Okay. Let's take some arbitrary number so that we understand. So now, no longer 6. Somehow I am telling you, I'm giving you that gate is at 4.9 volt. Okay. Then can you tell me what is your threshold voltage, which is going to decide the region of operation of this particular MOS transistor? It is going to 4.9 minus 3, because 3 volt is the threshold voltage of the transistor. This is, by the way, this 3 volt of the threshold is a intrinsic property of a transistor. So the moment you choose, you go to market and you buy a MOS transistor, in that data sheet of the MOS transistor, you will be given what is the threshold voltage of that particular MOS. So you will know what is that threshold voltage, whether it's 3 volt or some other voltage, you will know. So from the data sheet, I have given you this voltage here. I've given you that voltage to be equal to 3 volt. So that means now my gate is at 4.9 and my threshold is 3 volt. So I subtract it. And what is the voltage I get from this? I get 1.9. Okay. Now, if 1.9 is my critical voltage, can you tell me when will the transistor enter into the saturation? When this drain voltage goes below this 1.9 volt, I will be into the triode region. And as long as this drain voltage is above this 1.9 volt, okay, above or equal to this 1.9 volt, I will be into my saturation region. There's no equation involved here. This is called intuition. It takes time to build this intuition, but you need to build this intuition. This voltage is what I call it as judgment voltage. It is, it's not there in any book. This is my terminology that I have given. So if you see here, we're almost, towards the conclusion. I'll quickly demonstrate the idea through an example. Okay, let's take a simple example and demonstrate the idea. So for example, what I gave you earlier was not the complete circuit. I gave you part of a circuit, just the MOS. In this case, I am trying to build a complete circuit and give you an idea of how it is implemented. So given the transistor is on, threshold voltage VT, in this case, I have taken it as 2 volt from the data sheet. The gate is at 3 volt, the drain is at 2.5 volt, and the source is at 0.5 volt. Now you may ask, sir, how did you get these voltages? Okay, this is an electric circuit, okay, electric network. And we need to know how to solve this particular electric network. It has nothing to do with electronics. It is your basic circuit theory. Okay, you have to use the circuit theory principle to solve for this 3 voltages. And those of you who are familiar with your simulators, you know that dot DC or dot OP analysis. Okay, that's what does that analysis does that. Okay, you just do the mathematical simplification of the equations governing these principles, and you will get these voltages. In simulator, the simulator will directly give you these voltages. Okay, and that is why I'm telling you equation is not needed in a true sense, because if I have to analyze this, right, I'm not going to go down and write the MOS equation and the KCL KVL of this and try to solve it. No, I'll simply run DCOP in simulator, Spectre or Eldo or Spice, any such simulator. It will directly tell you what are your drain, gate, and source voltages. So now I know all these voltages. In this case, I have given you. Can you tell me what is the region of operation of the transistor? Let's try to build it intuitively. So objective is only intuition, no equation. I don't care about equation. Okay. Basically, you got to feel the circuit. As I told you, as you feel towards your loved one, you have to have feeling towards circuits. I feel the circuits, and as long as you don't feel the circuit, you will never be able to intuitively think on it, build on it, or create something with it. So you have to feel the circuit. Let's see how I can go about having feeling towards the circuit. Judgment voltage. See, I told you this is the critical one, right? This decides everything, this judgment voltage. So let's see. So in this case, I don't care about source voltage. All I care about where my gate voltage is. This is at 3 volt, and my threshold is at 2 volt. So can you tell me what will be my judgment voltage? Gate voltage is at 3 minus the threshold voltage, which is 2, which is equal to 1 volt. So that means this 1 volt is my judgment voltage, or the critical point of analysis. So as long as this drain voltage is equal or above this 1 volt, I'm in saturation, okay, SAT. And the moment it goes below this, I'm in triode or linear. Okay, I'm in triode. So that means it is as simple as that. I did not write any equation, guys. I'm stressing the point again and again, because if you think in terms of equation, you will never be able to come up with your own circuit. You don't use equation to come up with a circuit. When you have to solve a particular problem using transistors, resistors, this is a circuit with one transistor. In reality, when you implement, there will be 10, 20, 30, even more than that number of transistors. And if you try to write equation for every transistor and try to think that you will come to that circuit or analyze the circuit using equations, you won't be able to do it. You have to feel it. You have to have the intuitive approach to a circuit, and that's the true application of engineering, and that's the approach of us electronics engineers. That is the right approach. Okay. So in this case, VD is 2.5 volt. What is my judgment or the critical voltage? 1 volt. Is 2.5 volt greater than this 1 volt? Yes, it is greater than 1 volt. So that means which region the transistor is in? It is in saturation region. That's all. As simple as that. So that means if I have to design this as an amplifier, I want the transistors to be in saturation region. So that means if this is at 2.5 volt, is it the right thing for the circuit? Yes. As long as it is above 1 volt or equal to 1 volt, I am in saturation region. And that is what I want for it to be an amplifier. Now, how is this going to be an amplifier? That is the next level, which I will cover later. May not be in this circuit, in this presentation. But all I'm trying to give you here is the intuition. So the judgment voltage is 1 volt. If VD is greater than or equal to the judgment voltage, you are in saturation. If VD is less than the judgment voltage, you are in triode. In this case, VD, which is 2.5 volt, is above that threshold voltage, judgment voltage 1.1 volt. In this case, your VD, which is 2.5 volt, is above that judgment voltage, which is 1 volt, correct? So that means the transistor is in saturation. You see, I did not use a single equation to tell you what is the operating region of this transistor. And this is one such example. The entire field of electronics is filled with these approaches. As an engineer, we can never use equations to solve it. There are many reasons to it. Number one, the circuit itself could be very complicated. It is humanly not possible to solve everything by equation. And that is the reason you have all the simulators, right? SPICE simulators, ELDO or Spectre, all the simulators. Cadence is a company which has developed all the simulators. And those are the things that is used in the industry. We use those simulators in the industry. And second reason is the basic equation that you study in the book, right? The NMOS, that is just a first level of approximation, the square law equation that is given. First of all, that equation itself is complicated. And that too, it is very native equation. In reality, we use something called BSIM, developed in Berkeley. And that from there, the name comes as BSIM, okay? BSIM, BSIM model. So we use BSIM 4, which is a much more complicated equation to describe this particular one MOS. And like that, you have so many electronic components. So practically, it's not possible to solve anything with the equation. What we do is we come up with a circuit and we justify those analysis using those fundamental equations. Okay, maybe more on those equations. We'll talk about it in some other session. Now let me quickly switch gear and brief you about what are the opportunities that is there in terms of our electronic industry. So as you can see here, we have these are the I personally have been working in this core industry for almost 10 to 11 years, and I have done my master's in research from IIT Madras. So I have the complete background of what it takes in the core electronics engineering, and that is why I'm sharing these points with you. So broadly, if I have to categorize the entire industry of electronics core, right, it can be categorized in this few categories. One is radio transmitters. In this case, we talk about all this 3G, 4G, 5G, Wi-Fi, Bluetooth. By the way, this Bluetooth term is, when in my college final year, one of my friend was building this Bluetooth project, and I didn't know what Bluetooth is at that time. I asked him, "What are you building?" He said, "Hey, I'm building Bluetooth." And I couldn't believe him. I said that he's just joking, because Bluetooth for me, it was like blue colored tooth, and what is he building out of it? I had no idea that this is a communication protocol, and I just still remember how funny that was. And at the end of the day, it was fun of me and nothing funny. But ultimately, that was a moment that I remember, and that is why I highlighted this Bluetooth. So all these communication protocols that you are familiar of, they come under this radio. And here in this radio, we design transmitters, we design receivers, and this is where all the radio frequency comes into the picture. All those high frequency gigahertz transmitter, receiver, everything comes in this category. Then you have precision ADCs and DACs. ADC stands for analog to digital converter. DAC stands for digital to analog converter. Here, basically, right now, let's say I'm talking, right, and it's getting converted into electronic signal, and that is getting transmitted through this digital medium. And finally, you are able to hear at your end. So all these things are done through these ADCs and DACs. It takes the analog interface, analog signal, and converts them into digital, and then again takes back the digital signal and converts them back into the analog, because human always interacts through analog medium. Okay. By the way, do you guys know what is the fundamental difference between when I use the term analog and digital? Okay. Maybe you can think of it. One is continuous in time, other one is discrete in time. Maybe sometimes later, okay? Not for this presentation. Okay. So power converters is another domain. I think we all have known about this, all this laptop and PC. There's a power converters, right? We use the chargers, and earlier days when you had the gaming PCs or personal PCs, there will be SMPS power converters at the back. You have chips to control those powers as well. And that is another category. Then you have processors and digital signal processors. This is where your microprocessors, microcontrollers, and DSP comes into the picture. By the way, those of you who do not like DSP, shift gear. DSP is one of the key important topic. Don't think that you are in electronics, so you don't need DSP. Even today, at my level, I need DSP almost on a regular basis. DSP is very important. You need to know the fundamental ideas of DSP. Again, when I say DSP is important, I don't mean all the mathematical rigor of this DSP. What I mean is the intuitive feeling and understanding towards signal processing. And this is the latest trend that is coming up. I think we all have heard about artificial intelligence, right? And neural network chips are the chips which is enabling those artificial intelligence. So now, okay, so when you hear the term AI, right, it mostly applies to the software side of it. You have heard about Python, R programming, and all those things. Those are the software interface to it. Now, when you try to implement those neural network or artificial intelligence programming in a normal microprocessor or microcontroller, right, it becomes very inefficient. It becomes very slow. It becomes very power hungry. It becomes not so efficient. You can implement. Ultimately, it is a program, so you can implement in even in any Pentium processor or any Intel processor also, no issues. But that's not optimal. Whereas the true essence of artificial intelligence come about when the entire processing becomes fast. And that is where there are dedicated chips which is getting developed. And that is what is this neural network chip that we develop here. Okay, so here you can see that. And finally, the COVID and its impact. Okay, see, these are the two quotations which are very close to my heart, and I truly believe in them. In a day, when you don't come across any problem, you can be sure that you are traveling in a wrong path. A quote by Vivekananda. And a similar philosophy, again stated by great scientist Albert Einstein. In the middle of every difficulty, there lies the opportunity. So basically what they're trying to say here is difficulties are and problems are good, and COVID is no exception. I do understand the impact of COVID, the health challenges and the risks and the impact to the entire world, to our country that is associated with it. But at the same time, with this problem also, there are some blessings hidden inside it. If I think from our industry point of view, right, because of this COVID, nowadays the drive has gone towards a lot of automations. And when it comes to automation, none of the automations can be done without electronic components. You need microprocessors, you need microcontrollers, you need RF communicators to do any such automation. And that is why this drive towards automation has actually driven your electronic industry much higher. Right now, every electronic industry is seeing a surge of demand in terms of their chips, in terms of their future prospects. So second thing which is important is the Make in India drive. This is an initiative taken by our government, and this initiative also is going to drive our industry in a very positive direction, because now the entire opportunity of chip development, any electronic product development is going to be towards establishment of India. So of course, with the new establishments, with the new firms that is coming up, you will have a lot more opportunities coming up. So that's why there is no point in feeling bad or feeling uncertain about our future. Okay, I being from the industry, I know that it has come with its own challenges, but the industrial growth in terms of electronics is going to happen in a more positive way. And finally, this is my end vision in my life. I want to see, before I depart from this world, I want to see my country, my country, India, at #1 position. Currently, we are at GDP somewhere 4th or 5th, but United States is #1. But there is a projection. There's a video on YouTube. Maybe you can go and refer, where they say that soon India is going to be at #2, and even later it is even going to take over the #1 position. And I want to contribute towards it, and I want to live till that day when I see my country at that position. And as an engineer, all of us have responsibility towards contributing to this particular goal. And India was, pre-British time, if you go back to the ancient history of India, we were #1 country. We are the richest, and we will claim our position again in the future. And I want to contribute towards that. And with that, let me conclude my talk.